Salam and welcome everyone. Salam and welcome everyone. So today I am just compiling a bunch of shorter videos from my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the change in molar Gibbs energy of a perfect gas when its pressure is increased isothermally from 50.0 kilopascal to 100.0 kilopascal at 500 Kelvin. So the first thing we have to do is for us to write out the parameters. So I'm going to reread this and write that out. We're told to calculate the change in molar Gibbs energy. So what this is telling us to do is for us to determine the change in molar Gibbs energy. So that's what we're going to be solving for and of a perfect gas. So this is a perfect gas question when its pressure is increased. So that means we have increased isothermally. So that means we have an initial pressure and a final pressure because of the pressure increase. So from 50.0 kilopascal and then to the final pressure, which is 100.0 kilopascal at 500 Kelvin. So the temperature is 500 Kelvin. So I wanted to quickly mention that this is an isothermal question where there's a pressure increase. So the change in temperature is zero, or basically the temperature is constant throughout the entire process. So in an isothermal question where we're supposed to calculate the change in Gibbs energy or the change in molar Gibbs energy, the formula we're supposed to be using is this one right here, which is the molar Gibbs energy at the final pressure, okay, is equal to the molar Gibbs energy at the initial pressure, okay, plus RT ln the P final divided by the P initial. So the molar Gibbs energy at final pressure equals to the molar Gibbs energy at the initial pressure plus the gas constant times temperature times ln P final divided by P initial. So how you would get this, how we're going to have to rewrite this formula to be able to equate it to the molar Gibbs energy. So this is just going to look like the molar Gibbs energy of the final pressure at the final pressure minus the molar Gibbs energy at the initial pressure is actually going to be RT ln P final, okay, divided by P initial. So that would just be the change in the molar Gibbs energy, okay, equals to RT ln P final divided by P initial. So that's basically how this is done. Now, the next thing you have to do is just basic math. We're just simply supposed to substitute. So the change in molar Gibbs energy is just going to be RT. So R is going to be the 8.3145 joule per mole Kelvin. Now, I wanted to quickly mention something. You already know that we have two different values for gas constant. We have the 0.08206 as well as 8.3145. We're going to be using the 8.3145 because the unit for change in Gibbs energy or just any energy unit is in joules. So we're looking for the change in molar Gibbs energy. So what we're actually supposed to have is our answer in joule per mole or kilojoules per mole. So we have to use the units of the gas constant where it's gonna actually match the actual unit we're supposed to get for the answer. So that's why we cannot use 0.08206 because that's not the gas constant that I use whenever you're trying to get the energy unit. So that's why we're gonna be using this one times the temperature. We know that to be 500 Kelvin. Okay, times ln the P final. We know that to be 100.0 kilopascal divided by P initial, which is 50.0 kilopascal. So, of course, we cancel out the Kelvin, cancel out kilopascal, cancel out kilopascal. So, what is going to end up happening is this. We're just going to input this information in our calculator where we have 8.3145 joule per mole times 500 times ln 100 divided by 50. We can actually just cancel this out. 50 here, 1, 50 here, 2. So let me say that again. We're going to be putting this information in a calculator, 8.3145 joule per mole times 500 times ln 2. And when we input that information in our calculator, we end up getting 2,800 and 1.586 joule per mole. And that's basically the answer to this question. But of course, because we are chemists and in chemistry, there are laws and they're just better ways to us to manage our question. The first thing we have to notice is this: we have our answer in joule per mole, which is actually correct, but because of we're dealing with Gibbs energy, just like when we dealt with enthalpy, we like our work in kilojoules per mole rather than in joules per mole. So what's gonna happen is we're gonna go from joules per mole to kilojoules per mole, and we have 1000 joules equals 1 kilojoule. So to go from joules per mole to kilojoules per mole, we're just going to divide by 1000. So the change in molar Gibbs energy becomes 2.88156 kilojoule per mole. Now, we're still not done, right? We're still not done because we're also chemists and we like to make sure we have the proper number of significant figures for our final answer. So we go back to our work. We have 50 point zero kilopascal. This is 3 sig figs. Okay, we've got 100.0 kilopascal. This is 4 sig figs, and we have 500 Kelvin, which is 3 sig figs. The rule in chemistry is that we're going to pick the lowest number of significant figures based on the information we're given in our question, and we're going to use that to determine the number of sig figs for our answer. So we have to actually do this in 3 sig figs. So we're going to stop here. So rewriting this, what we actually have is our final answer is going to be change in molar Gibbs energy. It's actually 2.88 kilojoule per mole. So that's basically how you answer this particular question. If you have any question, please put in the comment section. If you have any concerns as well as suggestions for topics I should cover on this channel, or if you have a particular question you want me to solve, make sure you put in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the change in the molar Gibbs energy of a perfect gas when its pressure is increased isothermally from 1.0 atm to 100.0 atm at 298 Kelvin. So the first thing you have to note is that we're asked to find the change in molar Gibbs free energy. So that's basically what we're looking for. So that's going to be change in GM. Okay, so that's what we're asked to find of a perfect gas. So we're doing the perfect gas when its pressure is increased isothermally. So isothermally meaning the change in T is zero, or we have just one temperature throughout the entire process, meaning the temperature is constant throughout the entire process. So from 1.0 atmosphere, so we've got the P initial to be 1.0 atmosphere, and then the P final to be 100.0 atmosphere at 298 Kelvin. And we're also given the temperature. So that's 298 Kelvin. So we're basically asked to find the change in molar Gibbs energy. So the first thing you have to do when you have this is for you to realize like what formula you're supposed to use after you have written down the information given. And the formula for this type of question is the molar Gibbs energy for the final pressure, okay, equals to the molar Gibbs energy for the initial pressure, okay, plus RT, so gas constant times temperature, ln P final, okay, final pressure divided by P initial, the initial pressure. So that's basically what it is. Now, to be able to like rewrite this formula, so we have the change in molar Gibbs energy, you have the molar Gibbs energy at final pressure minus the molar Gibbs energy at the initial pressure is going to equal RT ln P final, okay, divided by P initial. So you note this. The molar Gibbs energy of the final minus the molar Gibbs energy of the initial is just simply, let me change the color. It's just going to be change in GM, which is what we're solving for, equals RT ln P final divided by P initial. Now we've gotten the equation we're supposed to use. We can just simply substitute. So you have change in GM, okay, equals RT. Since this is a molar Gibbs energy question, equation, and this is a question we're going to be using the gas constant 8.3145 joule per mole Kelvin, because the unit for change in molar Gibbs energy is just going to be joule per mole or kilojoule per mole. So I just wanted you guys to note, because that understanding of the units of what we're solving for is going to determine the gas constant we're supposed to use. So we're going to end up with 8.3145, okay, joule per mole Kelvin, okay, times temperature, which is T, which is 298 Kelvin. So that will be times 298 Kelvins. ln, okay, P final, we know that to be 100.0 atmospheres, okay, divided by P initial, which is just 1.0 atmospheres. So, of course, We cancel out the atmosphere, cancel out atmospheres, cancel out the Kelvin, cancel out the Kelvin. Now, I wanted to quickly mention something that not everybody might know. It's very, very important for you to note that since we're dividing between two pressure units, we actually don't need to change from atmospheres to pascals or to Newton per meter square, simply because we're going to cancel out the pressure anyway. So whatever conversions we do, maybe if we go from atmosphere to pascal, is really not going to have any effects when you do division. So we can as well leave our units in the original form, which is atmosphere. Because I know usually whenever you're dealing with canceling stuff out in chemistry, normally you're supposed to actually be canceling stuff out, but you have to convert to the units first. But in this case, we're just canceling between two pressure units, so we don't actually have to change the units to the units that would not originally work for this question, since we're just simply canceling out the units anyway, so the value is going to be the same. So the change in molar Gibbs energy is just 8.3145 joule per mole times 298 ln 100 divided by 1 would just simply be 11,410.33 joule per mole. Now, this is like the answer you're supposed to get. But one thing you have to understand is that whenever you're looking at whenever you're dealing with like Gibbs energy, it's important for you to know that Gibbs energy as well as enthalpy are usually written in kilojoules per mole. So what we can do is for us to convert this to kilojoules per mole. So what we end up with is going to be the change in molar Gibbs energy is going to be 11.41033 kilojoule per mole. And this is basically the answer to our question. But one thing you're also supposed to put in mind whenever you're dealing with a chemistry question is for you to look at how many significant figures, whenever you're dealing with questions that involve multiplication, that is given in the initial question. So we see that we've got two significant figures for 1.08 atmosphere. We've got four significant figures for 100.0 atmosphere. We've got three sig figs for the temperature value. So what you're supposed to use is the lowest number of significant figures, and that's going to be the answer. So we have to make sure we put 11.41033 kilojoule per mole in two significant figures, because two sig figs is the lowest number of significant figures. So the change in molar Gibbs energy actually becomes 11 kilojoule per mole. So this is basically the answer to this question. If you have any questions, please put in the comment section. For those of you who don't know, I'm actually an online tutor for STEM students who are trying to succeed in all their STEM related courses, whether they're in middle school, high school, or college. So if you're a student who is struggling or who is trying to improve your current grade in your class, email me at shahabitutoring@gmail.com. I'm also a mentor for students who are also struggling to navigate their academic career. So make sure you also email me at shahabitutoring@gmail.com. If you have any questions, don't forget to put in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the maximum non-expansion work per mole of CH4 that may be obtained from a fuel cell in which the chemical reaction is the combustion of methane under standard conditions at 298 kelvins. It's very important for you to know that whenever you're asked to find a question like this, the maximum non-expansion work, and you also hear under standard conditions, know that the work that you're talking about is just simply equal to the Gibbs energy of reaction. So that is basically what you're supposed to use. So you're going to use your knowledge of the Gibbs energy of reaction to actually solve this question. This is how it works. All of this information that you're telling you, this is just to like put more like just basically jumble up. They could as well just ask you to find the they could as well just ask you to calculate the Gibbs energy of reaction for the combustion of methane, and that's just it. That's literally what you're asking you to do. But this way they said work per mole. So it's just basically this. So understand that under standard conditions where the pressure and the temperature, and now you're hearing non-expansion and the volume is unchanging, note that the non-expansion work per mole is equivalent or equal to the Gibbs energy of reaction. So we know the general formula for the Gibbs energy of reaction, okay, to be the summation, okay, of the Gibbs energy of formation, okay, for the product, okay, minus the Gibbs energy of formation for the reactants. So that's basically how it's done. That's basically the formula that we're going to be using. And we're also told that of CH4 that may be obtained, calculate the maximum non-expansion work per mole. Okay, we know that of CH4 that may be obtained from a fuel cell in which the chemical reaction is the combustion of methane. So combustion reaction is just the reaction between whatever we're given, in this case CH4, okay, we're going to react it with oxygen to get or to form carbon dioxide gas and water, so H2O liquid. So that's basically how it's done. So CH4, of course, is a gas, methane gas. Oxygen is also a gas. So we're going to balance this chemical equation. And when we balance it, we see that we have to balance the hydrogen. We've already balanced the carbon, but we have to balance the oxygen. So you have, this is the balanced chemical equation. So from this information right here, we can start working. We're going to first of all organize this reaction according to the formula up top, where we focus on the Gibbs energy of reaction. So we're going to first of all work on the products, where we know that the formation, okay, the Gibbs energy of formation of the first product here is CO2 gas. Okay, so that's basically this one right here, plus the Gibbs, because of course the summation information is saying we're going to add them up. So for all of the products first, so the Gibbs energy of formation for the second product, which is 2H2O liquid, minus, now we focus on the reactant, where we have the Gibbs energy of formation for the first reactant, which is CH4 gas, plus the Gibbs energy of formation for the second reactant, which we know to be 2O2 gas. Now, I want to quickly mention something very important. You see this V here and this V here, they represent the coefficient of the products and reactants compounds. So in this case, we have the coefficient for CH4 to be 1, the coefficient for CO2 to be 1, but we have the coefficient for both O2 gas as well as H2O liquid to be 2. So we have to put that into consideration, meaning we're going to have to rewrite our formula in order for us to take those that information into account. The Gibbs energy of reaction becomes, okay, 2, sorry. So the Gibbs energy of reaction becomes, change the Gibbs energy of formation for CO2. We're going to rewrite this one again because, of course, that's not the stuff that has the coefficient. So plus 2 times the Gibbs energy of formation for H2O liquid. So what we're actually just redoing here is to take into account all of this all of the coefficient. That's all we're redoing. We're just taking into account all of the coefficient. So yeah, so minus, we do the same thing here. This one has no coefficient greater than 1, so we don't have to say 1 times. We can just rewrite it. So you have the Gibbs energy of formation, okay, for CH4 gas, okay, plus the Gibbs energy of formation of 2CO2 would just be 2, okay, times the Gibbs energy of formation of O2 gas. So this is basically how it's done. So that's basically how you do this. So of course, now we can comfortably substitute. For those of you who don't know, I'm going to be using the resource section of my physical chemistry textbook. And that is basically how I'm going to be able to like solve this. So the resource section of the physical chemistry book has all of the standard Gibbs energy of formation for all of the compounds. So you make sure you like look at it. But for anybody who doesn't have their textbook handy, let me just write all of that information for you. So the Gibbs energy of formation would, for all of them, would be this. So now that I've successfully written all of it, we can just simply substitute. So, but make sure that like you always have your textbook handy just in case of next time or in case you have another question that you have to do. So you have CO2 for the one for gas, you have negative 394.36, okay, kilojoule per mole, okay, plus 2 times the one for water is just negative 237.13 kilojoule per mole, okay, minus, so we're gonna do the one for CH4, so minus the Gibbs energy of formation for CH4, we know that to be simply negative 50.72 kilojoule per mole, plus 2 times the Gibbs energy of formation for O2 gas will just simply be 2 times 0 because that's what we have here. So 0 kilojoule per mole. Of course, now we have all of this information. We can just do the math. So the Gibbs energy of reaction becomes negative 394.36 kilojoule per mole, okay, minus 474.26 kilojoule per mole. And then here you've got minus and then minus again. So minus minus will give you plus. So this would be plus 50.72 kilojoule per mole. So plus 2 times 0 is 0, so you don't have to write plus 0. So you can just basically input all of this information in your calculator. You have negative 394.36 minus 474.26 plus 50.72. So that's going to simply give it Gibbs energy of reaction becomes negative 868.62 kilojoule per mole plus 50.72 kilojoule per mole. So the Gibbs energy of reaction becomes negative 868.62 plus 50.72 would give you negative 817.90 kilojoule per mole. And as you're aware, in chemistry, anytime we're done with the calculation, we have to make sure that we're putting the right number of sig figs or decimal places. And we're dealing with additions here, so we're going to focus on decimal places. We see that this first information, we have two decimal places, two decimal places, two decimal places, and we're supposed to pick the lowest number of decimal places according to the decimal places rule in calculations, especially in chemistry. So we have our answer in two decimal places. So our actual answer is just basically what we got. I want to quickly mention something so there's no confusion. I saw in some calculations online that people are given the absolute value of negative 817.90 kilojoule per mole, and they're turning that negative to positive. So I know a bunch of students can watch this video. I am a chemistry major, physical chemistry major. I'm sorry, chemistry. I'm done with university, but I studied chemistry, pure chemistry in college. And I know that there are other students in engineering and in physics that may be doing it. So I don't know, maybe it's a difference in the course of study that you're doing where you're maybe required to use absolute values. But for this question, I'm just going to give it the pure value, which is just basically negative 817.90. Make sure you ask your teacher for more understanding. So like I said, make sure you ask your professor. I think part of the reason why people are using the value though personally is because they're asked to calculate the maximum non-expansion work per mole because it's a non-expansion work and the reaction is basically what is creating the work like through the fuel cell. Maybe that's the reason why our value is negative because work is negative when the system is doing the work and it's positive when the surroundings is doing the work. So the pure value is negative, but the reason why maybe they're putting the absolute value is because they want to be able to say this amount of work was done, not necessarily. And when you say this amount of work was done, you don't put a negative there, you leave it, you make it a positive. But if you're just talking about the pure value, like in this case, it's a negative. But don't rely on just what I've said. Please ask your physical chemistry professor and do more research. I wish you guys all the very best. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, calculate the maximum non-expansion work per mole of C3H8 that may be obtained from a fuel cell in which the chemical reaction is the combustion of propane under standard conditions. So the first thing you have to note is calculate the maximum non-expansion work per mole. You're asked to find the work per mole of C3H8, which is propane gas, that may be obtained from a fuel cell in which the chemical reaction is the combustion of propane under standard conditions. So we're told to calculate the maximum expansion work. For any of you who don't know, this is just a trick question. Indirectly, what they're asking you is for you to determine the standard Gibbs energy of reaction is the same thing as the maximum, okay, non-expansion work. So there isn't one particular formula to necessarily determine this in terms of non-expansion work, right? It is just simply them using another synonym for this maximum non-expansion work, which is simply the standard Gibbs energy of reaction. That is basically what you're trying to tell us to solve. If you look at your physical chemistry Atkins textbook, you're going to see that this information, maximum non-expansion work per mole, okay, is the same thing as calculating the standard Gibbs energy of reaction. So that is it. Now, I wanted to also say that they said there is a chemical reaction, which is the combustion of propane under standard conditions. Well, important again for you to note that this is a combustion reaction. So that's going to be C3H8. Okay, it's going to be reacted with oxygen to form the real combustion reaction. Anytime you're dealing with combustion of organic compounds, is just note that that organic compound reacting with oxygen is always going to give you carbon dioxide and water. So that is it. So we have C3H8 gas we have oxygen gas, we have carbon dioxide gas, and we're going to end up with water as a liquid. So that is basically what we're doing here. Now, of course, the next thing we do, like we do in every chemistry question, is to simply balance the chemical equation. So you have a 3 here to balance the carbons. Then you have H8. Well, you have 8 hydrogens. You have 2 here. You're just going to put a 4 here to balance the hydrogens. So you have the carbon and hydrogen balance. Now you just have to deal with the oxygen. You've got 6 oxygens here. And you've got 4 oxygens here. So you just put a 5 here to balance the 10 oxygens on the right. So this is the balanced chemical equation, which is just C3H8 gas plus 5O2 gas would give you 3 molecules of carbon dioxide gas and 4 molecules of hydrogen gas. So now we've written this down. The next thing we have to simply do is to find the standard Gibbs energy of reaction for this reaction we just wrote based on the chemical equation. So that's it. Now, for any of you who don't know, the standard Gibbs energy of reaction, okay, the formula for it is just simply the summation, okay, of the Gibbs energy, okay, the change in Gibbs energy or formation or whatever you want to call it. Let me just draw it here. So the Gibbs energy of formation for the products, okay, minus the summation of the Gibbs energy of formation for the reactants, where the value for V is basically the coefficient for products, okay, here, and the value for V on the right is the coefficient for reactants. So that is it. So next, what we're going to do is we're going to apply this formula to this particular chemical equation. So you have the formation, the standard formation for the product side. So we're going to deal with the first product, which is just 3CO2 gas, okay, plus the formation, the Gibbs energy of the Gibbs energy of formation of the second product, which is just 4H2O, according to this reaction, okay, minus, okay, let's scroll up, minus the Gibbs energy of formation for the first reactant. So the Gibbs energy of formation for the first reactant, which is simply C3H8. So that would be C3H8 gas, of course, plus the Gibbs energy of formation for the second reactant, which is just simply 5O2 gas. So that would be 5O2 gas. So this is basically our work. Now, I wanted to quickly also mention this to you guys. This is the first organization. We have to reorganize this again a second time. And the way this is just for you to bring out the coefficients that isn't one. So if there's a coefficient in front of any of the compounds, you have to bring it out, except if that coefficient is one. So what I'm saying is that you say 3 times the Gibbs energy of formation for CO2, okay, for CO2 gas. That's how you do it. Plus 4 times the Gibbs energy of formation for H2O liquid. Okay, that's what we're doing here because we want our work to be very neat and I want it to be easy for you guys to understand. Here, the coefficient is 1, so we're just going to rewrite that. So it gives energy of formation for propane gas, so C3H8 gas, plus 5 times the Gibbs energy of formation for this last reactant. So that would be just O2 gas. So that's it. The next thing you, of course, do is for you to substitute. But before we go further, I wanted to tell you guys that I'm using the Physical Chemistry Atkins 11 edition textbook. And in the textbook, we have all of the Gibbs energy of formation values in the resource section of this textbook. So I am just going to be using the values from my textbook. But because I want it to be easy for you guys to follow along, I am just going to write out all of the Gibbs energy of formation for all of these molecules, the 4 molecules we have. So now I'm done writing the values. I advise you to pause this video and actually just write out the values because I have my notes with me and I'm not going to be going back and forth, back and forth, back and forth to this page to be able to continue working with this problem. So I'm just gonna skip doing that. Okay, like I'm not gonna be doing that the entire problem. So just make sure you pause this video and answer it. So we have this right here. So you change in Gibbs standard Gibbs energy would just simply be 3 times the Gibbs energy of formation of CO2. We know that to be negative 394.36 kilojoule per mole. Okay, plus 4 times the standard Gibbs energy of formation for H2O. So that would be 4 times standard Gibbs energy of H2O. That would be 4 times negative 237.13 kilojoule per mole, minus the standard Gibbs energy of formation for C3H8 will be negative 23.49 kilojoule per mole, okay? Plus the standard 5 times the standard Gibbs energy of formation for O2 gas would be 5 times 0 kilojoule per mole. So yeah, now I hope you guys have written it all out. So you have the standard Gibbs energy of reaction to be 3 times negative 394.36 kilojoule per mole is same thing as negative 1183.08 kilojoule per mole. Okay, that's one, plus 4 times negative 237.13 kilojoule per mole. That will be negative 948.52 kilojoule per mole. Okay, minus is just simply plus 23.49 kilojoule per mole. And then plus 5 times 0 is just simply 0. So just say plus one large 0. So the change in standard Gibbs energy of reaction will be negative 1, okay, negative 1183.08 kilojoule per mole minus 948.52 kilojoule per mole plus 23.49 kilojoule per mole. So you just simply input all of this information in your calculator to get the standard Gibbs energy of reaction to be negative 2108.11 kilojoule per mole as the answer to this question. So this is basically the answer to the question. Let's first of all go back to our question to make sure that we put in the proper number of decimal places, because we're always supposed to put in the proper number of decimal places in chemistry. So we look at the decimal places of what we used. We have 2 decimal places here, 2 decimal places here, 2 decimal places here. Then our answer is actually in 2 decimal places. So this is correct. I want to quickly mention something so that there isn't any confusion. I have noticed that in some questions, some answer or some solutions on the internet, they use plus 2108.11 kilojoule per mole instead of negative. So I think this point is, and I explained this in my other video where I had the first version of this question where we did the combustion of methane gas, and then this one we're doing the combustion of propane gas. I explained that it's possible that maybe some of you you're not taking this question as a chemistry major like I did. You're not taking this this course, physical chemistry, as a chemistry major. But you're taking it as something else. So what I'm trying to do for mine is negative 2108.11. I am doing this question based on the fact that I know the fuel cell does work, right? Meaning it ends up having negative, having lesser energy, while the people who may be using plus 2108.11 may actually be trying to say that this amount was of work was done. So they don't actually put a negative in front. While I am also saying that even though this amount of work was done, it was done by the system. So the system has lesser amount of energy. That's the reason why I'm putting negative. Some other people would put an absolute value and put a positive there to just tell you that this is the value of work done, while I'm giving you the raw data that not only was work done, there was a deficit because the system did the work. So I think that's the difference. If you don't understand what I'm saying, just rewatch what I've said. But if you want further explanation, please do your research or ask your professor to explain the reason why someone else might put absolute value on this value and end up having positive 2108.11, and why somebody else might decide to leave your answer in negative 2108.11. I'm choosing to leave my answer in the raw value. So if you have any questions, please put in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, suppose that 6.0 millimole of perfect gas molecules initially occupied 52 centimeter cube at 298 kelvins and then expands exothermally to 122 centimeter cube. Calculate the change in G for this process. So of course, because we are dealing with a science-based question or chemistry question, we're going to first of all write out all the parameters that we're given in order for us to determine what to do. So we're told the number of moles is just simply 6.0 millimole or let's just say 6.0 times 10 raised to the power negative 3 mole, okay, of perfect gas molecules, okay, initially occupies 52 centimeter cube at 298 Kelvin. So we have an initial volume to be 52. Let me rewrite that. 52, okay, centimeter cubed, okay, at 298 Kelvin, and then expands isothermally. So we have the final volume to be 122 centimeter cubed. And then we're told that this is an isothermal question. So that means the temperature is constant throughout the entire process of expansion. And that value for temperature is 298 Kelvin. So calculate the change in G for the process. So we're asked to find the change in molar Gibbs energy. So the first thing you have to know is when you're dealing with an isothermal expansion problem, you have this formula. You have the change in G, okay, of M. This is what I have of the final pressure, okay, equal to the change in G of the initial pressure, okay, times RT, plus, I apologize, not times, plus RT ln P final divided by P initial. Now, the problem with this question is this. First of all, we're not giving any value for pressure, and we're also given a value which is just the change in G is what we're supposed to look for. We're not supposed to look for the change in molar Gibbs energy. So those are the two issues that we've come across. But since it's a perfect gas question, we can convert and find the initial pressure as well as the final pressure based on the parameters we have, right? For example, we have the initial volume, we have the temperature being constant, we have the number of moles. That means we can find the initial pressure. So this is the formula we're going to use, but we need to make sure we have all the proper values that is necessary for this question. So what we're going to be using is just the perfect gas law. So PV equals nRT is what we have. So that's just going to be PI, VI, the temperature, the gas constant, number of moles is constant. So that's actually just going to be P initial is equal to nRT divided by V initial. So this is it. But the issue we have is that we're given our answer in centimeter cube. Sorry, our initial volume in centimeter cube when we're supposed to actually have that in decimeter cube. So we're gonna have to convert from centimeter cube to decimeter cube because the gas constant we're going to be using is going to be in decimeter cube. So we're going to go from centimeter cube to decimeter cube. So we know generally, I know that I've been doing a lot. I promise you it's gonna make sense. We know that one um decimeter is the same thing as 10 centimeter. So 1 decimeter cubed is going to be how many centimeter cubed? Sorry. It's going to be how many centimeter cube? I don't know what's up with the pen. So that would be 10 centimeter cubed, all of that. So that would be 1 decimeter cubed equals 10 times 10 times 10. That's 1,000 centimeter times centimeter times centimeter. That would be centimeter cubed. So you have that, and you have the 52 centimeter cube, so that would be 52 centimeter cubed, so that will be equals to that. So that's just, let's just call this unknown x, because of course we're trying to find what this value is. So we have 52 centimeter cubed, that's just going to be 1000 centimeter cubed x equals 52 centimeter cubed times 1 decimeter cubed. So that would be times 1 decimeter cubed. So that would be x is just simply going to be 52 centimeter cubed decimeter cubed divided by 1000 centimeter cubed. Of course, you cancel out the centimeter cubed, 52 divided by 1000. So x is just simply going to be 52 times 10 raised to the power of negative 3 decimeter cubed. Applying this knowledge to the final volume, we can just say the initial volume first is going to just be 52 times 10 raised to the power negative 3 decimeter cubed. Applying this knowledge to the V final is just going to be V final is actually going to be 122 times 10 raised to the power of 3 decimeter cubed. So I think that we get the point, right? So now that we have that, we can actually find our P initial. So yeah, we can find the P initial. Let's go into the next page. So P initial is equals to nRT V initial. This is a lot of work, I know. But that's the price you pay for learning. So that would be 0.08206, okay, dm cube atm, okay, divided by mole Kelvin, okay, times R. Sorry. That's R times, I forgot the number of moles, so I'm just going to add that here. So number of moles is just simply 6.0 times 10 to the power negative 3 moles. So times 6.0 times 10 to the power negative 3 moles, okay, times the temperature. We have that to be 298 kelvins, divided by the V initial, which we just converted. That would be 52 times 10 raised to the power negative 3 dm cubed. So 52 times 10 raised to the power negative 3 dm cubed. Of course, we cancel out dm cube, cancel out Kelvin, cancel out Kelvin, cancel out mole, cancel out mole. We have 6.0 times 10 raised to the power negative 3. We just cancel out the 10 raised to the power negative 3. Cancel that out. So what we actually have now, we're just going to input in the calculator. We have 0.08206 times 6 times 298 divided by 52. When you input that information in your calculator, we're going to end up getting 2.8216 atmospheres. And of course, we know from our combined gas law, anytime you have temperature constant, you have P initial, V initial equals P final, V final. So we're just going to basically find what's P final. So P final is just going to be P initial, V initial divided by V final. So that'll be P initial is just going to be 2.8216 atmospheres times V initial. We know that to be 52 times 10 raised to the power negative 3 dm cubed. So that would be 52 times 10 raised to the power negative 3 dm cubed divided by V final, which is just simply 122 times 10 raised to the power negative 3 dm cubed. Okay, when you cancel out the dm cube, cancel out dm cube negative 10 raised to the power negative 3 times 10 raised to the power negative 3, that will be 2.8216 atmospheres times 52 divided by 122. You're going to have the P final to become 1.2026 atmospheres. Yep, that's how it's done. So that's the P final. So now we have that. Now we can properly substitute, right? Let's remember that we got this formula here. So GMP, the molar Gibbs energy of final pressure, okay, equals to the molar Gibbs energy for the initial pressure plus RT ln P final divided by P initial. So that would be change in the molar Gibbs energy, because I'm actually going to have to put GMPF minus GMPI. So the final minus the initial will just give you the change in molar Gibbs energy equals RT ln P final divided by P initial, right? So that's how it's done. But then we have one issue. The issue we have is that we're not asked to find the molar Gibbs energy. We're not asked to find the change in molar Gibbs energy. We're asked to find just the change in Gibbs energy. So note this, okay? The molar Gibbs energy, okay? The molar Gibbs energy generally is just the Gibbs energy divided by the number of moles. You would get the change in molar Gibbs energy. So what this is telling you is this: for you to be able to get the change in Gibbs energy, you're going to have to cross multiply, and you have the change in Gibbs energy is actually going to be the number of moles times the change in molar Gibbs energy. So what you're going to do is you're going to times this equation right here. Let me call this equation 1. You're going to multiply this equation 1 by the number of moles. So let me write this here. Multiply, this is a lot, equation 1, okay, by number of moles. You're now actually gonna get the change in Gibbs energy, which is what you're actually solving for. So when we multiply equation 1 or equation I by n, which end up with n change in GM, okay, equals nRT, okay, ln P final divided by P initial. So we writing this is just going to be the change in Gibbs energy equals nRT ln P final divided by P initial. So the change in Gibbs energy is just going to be N, number of moles. Let's go back to our question. The number of moles is 6.0 times 10 to the power negative 3 mole. So that would be, let me write it in a different color, 6.0 times 10 to the power negative 3 mole, okay, times R. We're going to be using the gas constant 8.3145 joule per mole Kelvin, mainly because our units for any energy related value is going to be in joules. So Gibbs energy has to have the units joules. So we're going to be using this gas constant times temperature, which we know to be 298 kelvins according to the question. So 298 Kelvin here, and all of that times ln p final. We just solve for that. P final is this one right here, 1.2026. So 1.2026 atmospheres actually, okay, divided by what's this called, the p initial, which is 2.8216, divided by 2.8216 atmospheres. And I know some of you may be wondering, why didn't we convert from atmosphere to kilopascal? Well, because we're going to be like canceling out the atmospheres anyway in a question where we're just focusing on like it's ln into bracket the information with the pressure. It's not like we're multiplying pressure by another totally different value. We're just dividing between two pressures, so we can leave it at whatever units we want. So that's it. So we've canceled out the atmosphere. We're going to cancel out the mole. We're going to cancel out the Kelvin. As you're aware, since it gives energy, we're supposed to have an answer in joules. So the change in G, or the change in Gibbs energy, will be 6.0 times 10 raised to the power of negative 3 times 8.3145 joules times 298 times ln 1.2026 divided by 2.8216. So you're supposed to input all of this information in your calculator. But before we do that, let me break it down. Let's say 6.0 times 10 raised to the power of negative 3 times 8.3145 joules times 298 Kelvin. Putting that in our calculator, we have 14.86633 joules, okay, times ln 1.2026 divided by 2.8216 is just the same thing as 0.426212. So that's basically it. When you multiply them together, you end up with negative 12.6783 joules. That's basically the answer to this question. But then again, we are chemists and we need to make sure we put in the proper number of sig figs. So we have to go back to our questions to see how many significant figure is the lowest. So like when we look at our values, we're going to see the lowest number of sig figs and we're going to go with that. So we have 2 sig figs here, 2 sig figs here, 3 sig figs here, 3 sig figs here. So the lowest number of significant figures is simply 2 sig figs. So we're going to put our answer in 2 sig figs. So the change in Gibbs energy is just going to be negative 13 joules. So this is basically the answer that we're solving for. Like that's why we did this whole calculation. So hopefully this is easy for you guys. If you have any questions, please put it in the comment section. If you have any concerns, also put it in the comment section. Salam and welcome everyone. So today we're going to be doing the question on the screen that says, suppose that 2.5 millimole of a perfect gas molecules initially occupies 42 centimeter cube at 300 Kelvin and then expands isothermally to 600 centimeter cube. Calculate the change in Gibbs energy for the process. So the first thing you have to know is to write out your parameters. We're told the number of moles is 2.5 millimole of perfect gas molecules initially occupies 42 centimeter cubed. So that means we have the initial volume to be 42 centimeter cubed at 200 Kelvin, okay, and then expands isothermally. So we have an increase in volume. So there's going to be a V final to 600 centimeter cube. So this is an isothermal expansion problem, meaning the temperature is going to be constant throughout the entire process. So we're told the temperature is 600 Kelvin, okay? And of course, the change in temperature is going to be 0. And we're asked to actually solve the change in Gibbs energy. Now, I have solved a very similar question, but that took a lot of time. Now I'm trying to solve it to take less time. So make sure you watch how I solve this question with this method, and make sure you watch the other video in the description box to see how I solve it with the other method. So the first thing you have to note is all of that, what I've written. The next thing you know is that for a question that involves isothermal Gibbs energy, we have this general formula, which is just simply GM, okay, of the final pressure, okay, equals to GM, so the molar Gibbs energy of the initial pressure, okay, plus RT, ln the P final divided by the P initial. So with this method, we're not going to actually go find the value for the initial pressure or the final pressure. We're going to use our understanding of the initial volume and the final volume, as well as our knowledge of the combined gas law. So the combined gas law is just P1, okay, V1, or P initial, V initial divided by T initial equals P final, V final divided by T final. So because our temperature is going to be the exact same value, we're going to erase that. So we're not going to be using this. So what we end up with is P initial, V initial equals to P final, V final. So what's next is that for us to be able to manipulate this equation to what is going to be easy for us, we're going to actually put V initial and V final in terms of P final divided by P initial. So P final, okay, divided by P initial becomes V initial divided by V final. So we're gonna, when we have this particular information here, we can just simply substitute here since we're dealing with an isothermal problem anyways. So that's basically how it's done. So let me like fill this in. I apologize, my pen mistakenly erased this. So now we have this. So let me rewrite in the formula. Now we have the molar Gibbs energy of the um final volume, okay, is going to equal the molar Gibbs energy at the initial volume, okay, plus RT ln V initial, okay, divided by V final. Now, we were asked not to find the molar Gibbs energy. We're not asked to find the change in molar Gibbs energy. We were told to find the change in Gibbs energy. So rewriting this, we have, let's say, GM, okay, of V final minus GM of the V initial, okay, equals RT ln V initial divided by V final. So that would be change in GM. So yeah, change in GM is just going to be RT ln V initial divided by V final. I apologize, but this first part of the work just involves a lot of math. It's to make our eventual formula that we're going to be substituting our values into to be very, very easy for us to calculate with. So now you have this. Because we're asked to find the change in Gibbs energy and not the change in molar Gibbs energy that we have to apply our knowledge that the change in molar Gibbs energy is the same thing as the change in Gibbs energy divided by the number of moles. So to go from GM to to go from changing GM to changing G, we just simply cross multiply and we have the change in G to actually be the number of moles times the change in molar Gibbs energy. So the change in G of M. So because of course, we have an equal to here, we have to multiply this number of moles by this equation. So let's imagine this is equation 1. Just bear with me. We're just going to multiply, okay, equation 1 by number of moles. So when we do that, we end up with changing G, okay, changing G, which is what we're trying to do here, okay, is now going to equal nRT ln V initial divided by V final. That is basically the equation that we're going to use now to solve this question. So the next thing you have to do, of course, is for you to simply substitute. We have 2.5 millimoles. So we have the change in G becomes 2.5 times 10 to the power negative 3 moles. So millimoles times 10 to the power negative 3 moles times, we're going to be using the gas constant, 8.3145 joule per mole. Kelvin, because the change in Gibbs energy would have to have the units in joules. So we have to use the gas constant that matches the unit of what we're solving for, which is a change in Gibbs energy. So that times the temperature that we're given. Going back to our question, we see our temperature is 300 kelvins. So 300 Kelvin times ln V initial. We know that to be 42 centimeter cubed, and we know V final to be 600 centimeter cubed. So 42 centimeter cube divided by 600 centimeter cube. Of course, we cancel out the mole, the Kelvin, the centimeter cube, centimeter cube. And some of you may be wondering, why didn't we like convert centimeter cube to the proper volume unit for a question like this? Well, because we're just dividing by two volume two different volume, the initial volume and the final volume, and we're not actually multiplying what is inside the ln with any other information like pressure, temperature, number of mole gas constant, this is okay because we're just dividing by volume. So we're actually gonna have the correct answer. It's just like you saying, why don't I divide 1,000 grams divided by 2,000 grams? Well, 1,000 grams divided by 2,000 grams is 1 over 2. But guess what? 1 kilograms, which is equivalent to 1,000 grams, divided by 2 kilograms, which is equivalent to 2,000 grams, would also give me 1 over 2 because we're just dividing within the same exact information parameter, which is the volume. So this is not an issue because I know sometimes it confuse chemistry students and they ask me that question whenever I'm tutoring. So just simply having changing G is just 2.5 times 10 to the power negative 3 times 8.3145 times 300 times ln 42 divided by 600. We end up with 6.2358 joules, okay, times ln 42 divided by 600 is just 42 divided by 600 is just simply 0.07. So changing G, just 6.23588, okay, times ln 0.07 will end up giving us negative 16.5828 joules. So this is basically the answer to our question. But as chemists, we have to make sure that we have the proper number of significant figures based on the information in our question. We have 2.5 millimole. So two sig figs, two sig figs, three sig figs, three sig figs, and the lowest number of significant figures based on the numerical question values in our question is two sig figs. So we have to approximate this answer here in two significant figures. So we have the change in Gibbs energy is going to actually be negative 17 joules. So if you have any questions, please put in the comment section. If you have any concerns or suggestions for what I should cover, please also put in the comment section. I'm a tutor who helps students in all your STEM related courses to succeed and to improve. I also help with student mentoring for any of you that may be struggling. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, use the values of the relevant standard Gibbs energies of formation from the resource section to calculate the standard Gibbs energy of reaction at 298 Kelvin of the following reactions. The first reaction, and then we have another reaction. So I wanted to just quickly mention this. This is the B part. I've done the A part of this video. It is the Physical Chemistry Atkins textbook for anyone who is wondering. It's the 11th edition. So I wanted to quickly mention this. Looking at the question, we see that we've been told that we're supposed to use the resource section of our textbook to find the Gibbs energies of formation for the different molecules in this particular reaction and the second reaction as well. So we're supposed to have used those resource section information, the values there, to find the standard Gibbs energy of reaction. Now, to make your work easy and to make like tutoring you easy, I have decided to go on into the textbook and write out all of the Gibbs energy of formation values so that it's easier. So I advise you to pause this video now and to write all of this in your book that you're using while you're listening to this video. So now that you've written it, I am going to start explaining it. So generally, anytime that you're working with the Gibbs energy of reaction, you have to note that the general formula is the summation, okay, of the Gibbs energy of formation for the products, okay, minus the summation of the Gibbs energy of formation for the reactants. So you have to know this. This is such an important formula to memorize. So when you know this, then you'll be able to like start working. So you have this information right now. Now we have to like start with the reaction. So the first reaction that we're given is this one, zinc solid plus Cu2 plus would give us zinc 2 plus plus Cu solid. So I'm just going to rewrite it. Now, I'm not going to be going back and forth for each particular information. So make sure you pause it if there's anything you want to like have in your notes while I'm solving, because I already have my own notes and I'm going to be solving using my own notes. So you have zinc 2 plus, zinc solid plus Cu2 plus aqueous. Then you have zinc 2 plus aqueous plus Cu solid. So we have this now. I'm going to be organizing this particular reaction based on the formula, general formula I just taught you. So the Gibbs energy of formation for this particular reaction is going to be focusing on the products first. So you have the Gibbs energy of formation for the products, okay? The first product, which is Zn2 plus, okay, aqueous, plus, don't forget we have a summation, right? The second product, so the Gibbs energy of formation for the second product, which is Cu solid. Okay, so all of that information minus, now we're going to deal with the reactant side. The Gibbs energy of formation, okay, for the reactant, the first reactant, which is ZNS or zinc solid, plus the Gibbs energy of formation for the second reactant, which is copper 2 plus, so Cu2 plus. So you can see that we've properly organized what we have. So now, of course, we're just going to substitute. So what we're going to be substituting is this information right here. Like we're going to be substituting for the first reaction, that is, we're going to be substituting each one of this information right here. So yeah, that's why I told you guys to write it so it's easier for you. So the Gibbs energy of formation for Zn2 plus, according to the resource section of the textbook that I've written earlier and I showed you earlier in the video, we have that to be negative 147.06 kilojoule per mole for Zn2 plus, plus the Gibbs energy of formation for copper solid, we have that to just be 0 kilojoule per mole, or you can just say 0. So all of that information minus the Gibbs energy of formation for ZNS. So the zinc solid is just going to be 0. Okay. So the first product plus we're going to look for the um, Gibbs energy of formation for the second product, which is Zn2 plus. And looking at the research section of our textbook, we have 65.49 kilojoule per mole. Okay. So we just simply, rewriting this, we just simply have 147. Gibbs energy of reaction is going to be negative 147.06 kilojoule per mole minus 65.49 kilojoule per mole. So the Gibbs energy of reaction is just going to be simply negative 147.06 minus 65.49. When you input that information in your calculator, you end up with negative 212.55 kilojoule per mole. Now, we're not done because, of course, we're dealing with chemistry, right? When we deal with chemistry questions, we know that we have to go back to the first information we have and look at the values. We see that the lowest number of decimal places that we have from the values that we use in our calculation, for this particular one, we have 2 decimal places. For this particular one, we have 2 decimal places, and as well, this one we have 2 decimal places. That means our answer has to be in 2 decimal places. And luckily for us, our answer is in 2 decimal places. So this is actually the answer to this question. Now we move on to the second reaction, which is just simply combustion of sucrose. So C12H22O11 solid, which is just basically here. This is sucrose for anyone who doesn't know. This is the chemical or the molecular formula for sucrose. So that's that, plus O2 gas and plus 12O2 gas. So I'm rewriting what I showed you earlier. This is a combustion reaction of an organic compound. You're always gonna have carbon dioxide, okay, and water as the products. So balancing the equation, actually we're not really balancing, we're just repeating what we're given. Just looking at the equation, of course, is not balanced. So we have 12 CO2 here and we have 11 H2O here. So that is what was given to us, this reaction right here. So, of course, if you go back to what I taught you earlier, I'm just going to recap. The Gibbs energy of reaction is just simply the formation of the Gibbs energy of formation for all of the products, okay, minus the summation of the Gibbs energy of formation for all of the reactants. So you end up with the Gibbs energy of reaction is going to equal this one right here. So you have Gibbs energy of formation for the first products, you have that to be 12 CO2 gas plus Gibbs energy of formation of the second products, we have that to be 11 H2O liquid minus the Gibbs energy of formation for the reactant would just simply be energy of formation of the reactant would just simply be C12H22O11 solid. So that's that. the first reactant. Then the second reactant would be the Gibbs energy of formation of um 12O2 gas. So that's how it's done. Now I want to quickly explain something to you guys. This formula here, the V here and the V here, is just for you to take into account the coefficients that could possibly be in a particular reaction. So for the products and for the reactant. So for example, now we see the coefficient of this particular first reactant is 1. The coefficient for O2 gas is 12. The coefficient of CO2 gas is 12. And the coefficient of H2O liquid is 11. So I'm going to just say that so that you guys understand that's what the V stands for. And even though we have properly organized this, we still have to do further organization because we have the coefficients present. So we have to rewrite this to look like this, right? So we're going to bring out 12 here. So it's going to be 12 times the Gibbs energy of formation for CO2. And the reason is because we cannot in any way, shape, or form have the Gibbs energy of formation for 12 CO2. That does not exist. We can only have the Gibbs energy of formation for a compound, not the coefficient times the compound, right? Just the compound. So we have to bring out the coefficient, in this case 12, and rearrange it that way before we can like start to solve. So we have 11 here times Gibbs energy of formation for the compound, which is just H2O, okay, liquid. So all of that minus, do the same thing here. Here our Gibbs energy of formation is going to remain the same. Like this entire information will remain the same because we don't have a coefficient greater than 1 that we have to bring out. So it's just going to be this C12H22 or 11 solid. Plus, here we have a coefficient greater than 1. So we're going to say 12 times the Gibbs energy of formation for O2 gas. So that's basically it. So we have the Gibbs energy of reaction is just going to simply be 12 times Gibbs energy of formation for copper. I'm sorry, not for copper, for CO2, carbon dioxide gas. Is just based on what I have that I've written down from the resource section is 12 times negative 394.36, okay, kilojoule per mole. Okay, that's the first one, plus 11 times the Gibbs energy of formation for H2O liquid, which is just simply negative 237.13 kilojoule per mole. So that's the product side. And then you have minus Gibbs energy of formation for the sucrose, which is C12H22O11 solid. We have that to be negative 1543 kilojoule per mole. Okay. Plus the Gibbs energy of formation of O2, which is just 12 times the Gibbs energy of formation for O2. We see that to be 0 kilojoule per mole. So we have that information now. So we just simply, we just do the math, right? That's how it's done. So the Gibbs energy of reaction becomes 12 times negative 394.36 negative 4732.32 kilojoule per mole. Okay. Minus. So you have here, you've got plus and you've got minus here. So plus minus is just minus. So 11 times 237.13 is just simply 2608.43 kilojoule per mole. Of course, like I said, this is a product side. So then you have minus over here, okay? And then minus here, you're going to get plus. So I'm just going to say plus 1543 kilojoule per mole. So we have the Gibbs energy of reaction to equal negative 4732.32 kilojoule per mole minus 2608.43 kilojoule per mole. You're going to end up with negative 7340.75 kilojoule per mole plus 1543 kilojoule per mole. So continue. We just put this information on a calculator. Negative 4340.75 plus 1543 would give us negative 5797.75 kilojoule per mole. Now, I wanted to quickly mention something that this is like a really good time for us to note that in chemistry, we don't just leave our work just like this. Like, we don't just pick an answer whenever we calculate. We don't just find an answer whenever we calculate and just leave it like that. We have to make sure we put in the proper sig figs or proper decimal places. We see that the information that we have right from the beginning of our calculation is just this one, and this one. We can see the number of decimal places for this one is 2 decimal places. This one, 2 decimal places here. We don't see a point zero, but we know it's 1 decimal place because of math. If you say you have 5 is the same thing as 5.0. So we just assume it's a 1 decimal place situation. So we just end up here. So we have the Gibbs energy of reaction to be negative 5797.8 kilojoule per mole. And this is basically the answer to the second reaction. So now we've come to the end of this video. If you're a student who's watching this video and you're struggling, or you know someone who's struggling in school, I help students improve and succeed in all their STEM related courses, whether they're in middle school, high school, or college. I also help with student mentorship in order for them to properly navigate their academic life. So if you'd like to know more about my services, email me at shohabitutoring@gmail.com. I wish you guys all the very best. Make sure you like and subscribe. Don't hesitate to email me at shuhabitutoring@gmail.com. I wish you guys all the very best. Salam and welcome everyone. So today we're going to be working on the question on the screen that says use the values of the relevant standard Gibbs energies of formation from the resource section to calculate the standard Gibbs energies of reaction at 298 Kelvin of the following reactions. You have the first reaction, the second reaction, and the third reaction. Now, I wanted to first of all mention that I'm using the physical chemistry Atkins textbook. And in this textbook, they have a research section that has all of the formation that is basically needed for you to solve the questions in the book. So we're told to find the values of the relevant Gibbs energies of formation from the research section. And when we get those values, we should calculate the standard Gibbs energies of reaction at 298 kelvins. Now, the first thing you have to know is I've gone to my textbook and I've written all the relevant information that is needed. And the reason why I'm doing that is so that it's easier for you guys to be able to follow all that I'm doing for this particular question. I'm going to be going back and forth, back and forth, back and forth, so that it's easy for you people to like know what it is that I'm doing, right? So I wanted to say this that before we can go on to start using all of this information on this page, we have to understand the major formula we're supposed to use, which is the Gibbs energy of reaction, right? The standard Gibbs energy of reaction is equal to the summation of the Gibbs formation energies for the product minus the summation of the Gibbs energy of formation for reactants. So to begin, I'm going to start with the first reaction. We have 2CH3CHO, okay, gas, plus O2 gas, and then you have 2CH3COOH liquid. Now, I want to quickly mention something so no one is confused. I'm not going to be going back and forth in between pages because I already have this problem solved in my own personal note. So if you need to if you need to like rewind the video and pause it and write out all of the Gibbs energy of formation for each one of the substances or molecules or compounds in this particular question, then I would advise you to do so. But I'm not going to be going back and forth, except if it's absolutely necessary because I have my book. So, anyways, that's just one thing I wanted everyone to note. So you have 2CH3CHO gas plus O2 gas, and then you have 2CH3COOH. Well, applying the formula for the Gibbs energy of reaction, we have going to focus on the products first. So you have the formation, Gibbs energy of formation for the product, 2CH3COOH. Okay, liquid. Let's not forget. It's very important for you to know the phase that you're working with. So yeah, very, very important. So yeah, minus this one right here, which is the Gibbs energy of formation for 2CH3CHO gas plus the formation, Gibbs energy of formation of the second reactant, which is just O2 gas. So this is basically how you organize what you're dealing with right here. So now we're going to reorganize again. It's very necessary. It's for you to just have this right here. You bring out the 2 because the 2 right here is a coefficient, right? This 2 right here is also a coefficient. And the coefficient, you cannot find the Gibbs energy of formation of 2CH3COOH or 2CH3CHO, mainly because you can only find the Gibbs energy of formation for molecules or compounds. So what you're going to end up doing is you have to bring out the 2, just say 2 times the Gibbs energy of formation, okay, of each one of the compounds. So that's how you properly arrange it. But I like to do it step by step so everyone is on the same page and there's no confusion. So I'm going to do the same thing here 2 times the Gibbs energy of formation of this compound. So 2CH3CHO gas, okay, plus this one has no coefficient. Coefficient is 1, so no biggie. So that will be O2 gas. So yeah, that's basically what's supposed to be done. Now we can start to substitute. Like I said, I'm not going to be going back and forth in between these pages to write it all down. So if you need to pause this video and write all of this information, since I've already done more than half the work where you have like gone to the research of the textbook to give you guys these values, you can pause this video, write those values down, and then you can start to substitute. So you have this information right here. You have 2, okay, times the Gibbs energy of formation for CH3COOH for me. According to our research section, we have 389.9 kilojoule per mole. Okay, minus right here 2 times the Gibbs energy of formation for CH3. Sorry, this is a mistake. For CH3CHO gas, 128.86 kilojoule per mole, plus the Gibbs energy of formation for oxygen is just simply 0 kilojoule per mole, just 0. So yeah, we've done it for the second one. Now we have this. So the Gibbs energy of formation, the Gibbs energy of reaction is now going to be 2 times 389.9 kilojoule per mole is just simply 779.8 kilojoule per mole. Okay, minus 2 times 128.86, which is just simply 257.72 kilojoule per mole. So that's basically how it's done. So we're now going to input our information in the calculator. 779.8 minus 257.72 would give us 522.08 kilojoule per mole. So this is basically how this is done. Now let's not forget that when we're doing our work, we have to look at the proper number of decimal places. And we see that the initial information in the question, one of the Gibbs energy of formation is 1 decimal places. So it has the lowest number of decimal places. So we have to put our answer in that number of decimal places. So we have this answer here to be 522.1 kilojoule per mole. And this is basically the answer to this question. So now let's go to the second reaction. The second reaction is Ag, 2AgCl, solid, plus Br2, liquid, and then 2AgBr, solid, okay, plus Cl2, gas. So we have all of this information. Let's not forget the general rule is this one right here. We know that the Gibbs energy of reaction is just the summation of this is the coefficient, by the way, for all of you who don't know what this V stands for. It stands for the coefficient. So, sorry, let me change back to purple. So you have the Gibbs energy of formation, okay, for products minus the Gibbs energy, the summation of the Gibbs energy of formation for reactants. So that's basically the general formula for the Gibbs energy of reaction. So we have that, we have our reaction. Let us organize. So we have this one right here. We're going to first of all focus on the products. So you have the Gibbs energy of formation for the first product. So that'll be 2AgBr, solid, okay, plus the Gibbs energy of formation of the second product. So that would be Cl2 gas, okay, minus the Gibbs energies of formation of the first reactant, which is changing the Gibbs energy of formation for the first reactant, which is 2AgCl, solid, okay, plus the Gibbs energy of formation of the second reactant, which is bromine, liquid. So yeah, gives energy of reaction. So reorganize again. So we have 2 times it gives energy of formation, okay, of AGBR when we reorganize solid plus this one doesn't have any coefficient greater than 1. So we're just going to rewrite it here. So chlorine gas, then minus here we have a coefficient greater than 1. So we have 2 times the energy of formation of AgCl solid plus gives energy of formation for bromine liquid. So yeah, that's basically it. So the Gibbs energy of reaction would just be us substituting. So 2 times the Gibbs energy of formation for HBr. Looking at the resource section, we have negative 96.90 kilojoule per mole. Okay, plus the Gibbs energy of formation for chlorine gas. Well, that's just simply 0 kilojoule per mole. Okay, so that we're done with the product side. Now we're going to deal with the reactant side. 2 times the Gibbs energy of formation for AgCl solid. We have that to be negative 109.79 kilojoule per mole. And we have the Gibbs energy of formation for bromine liquid to just simply be 0 kilojoule per mole. Gibbs energy of reaction is just 2 times negative 96.90 kilojoule per mole. That's negative 193.8 kilojoule per mole. Okay, so just this. And of course, plus 0, so we don't have to focus on that. So this is the product side minus 2 times negative 109.79 kilojoule per mole. We know that to be 219, okay, 0.58 kilojoule. I'm about right kilograms, kilojoule per mole. Of course, plus 0, we don't have to write that down. So you have, sorry, that 2 times negative 109. So it's going to be negative 219. So just rewriting this, Gibbs energy of reaction becomes negative 193.8 kilojoule per mole, okay, plus 219.58 kilojoule per mole. You just simply put this information in the calculator to get 25.78 kilojoule per mole. And this is basically the answer to the question. Now, looking at our question, we're going to see that the lowest number of decimal places based on the values that we solved in this question, meaning the values that we were given at the beginning. So the formation for AGBR and the formation for AgCl, the lowest number of decimal places is 2 decimal places, and our answer is in 2 decimal places. So this makes this answer here our final answer. We don't have to manipulate anything. So yeah, that's basically how it's done. Now the third question, let me just do it on the last page. We have the equation Hg mercury, so HGl, okay, plus Cl2 gas, and we have HgCl2 solid. Let's not forget, same old information. We know that the standard energy Gibbs energy of reaction, the formula is the summation of the Gibbs energy of formation for all of the products, okay, minus the summation of the Gibbs energy of formation for all of the reactants. So that's basically how it's done. So the Gibbs energy of reaction is going to be equal to, for the products, we're going to do the product first. So let me just write that down. So you have the big bracket. So you have the Gibbs energy of formation for HgCl2 solid minus the Gibbs energy of formation for the reactant. So you have Hg liquid plus the Gibbs energy of formation of the other reactant, which we have to be Cl2 gas. Okay, so we've basically organized. You can look at this question, this particular part of the question. You can see that we don't have to organize twice because the reactant does not have a coefficient greater than 1, or neither does the product have a coefficient greater than 1. So HgCl2, every single one of those compounds or molecules have their coefficients to be 1. So we don't have to rearrange further. We can just simply substitute. So you have this right here. So you have it gives energy of formation for HgCl2 according to the resource section of our textbook, is just negative 178.6, okay, kilojoule per mole, okay, minus the Gibbs energy of formation for HGL, which is just mercury liquid, is 0 kilojoule per mole, okay, plus the other product, which is Cl2, the Gibbs energy of formation for chlorine gas is also 0 kilojoule per mole. So what's just going to happen is just us just having Gibbs energy of reaction will be negative 178.6 kilojoule per mole minus 0, which is just simply us just getting this answer, which is just negative 178.6 kilojoule per mole. So this is basically the answer to this question. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, estimate the change in Gibbs energy of 100 centimeter cube of water when the pressure acting on it is increased from 100 kilopascal to 500 kilopascal. Given that the mass density of water is 0.97 gram per cm cube, determine the change in molar Gibbs energy. So we're asked to find estimate the change in Gibbs energy. So this is what we asked to do. And then of 100 centimeter cube of water. So we're told the volume of water is 100 centimeter cube. Okay. When the pressure acting on it is increased from 100 kilopascal. So we have from, meaning there's an increased, right? From, meaning there's an initial value for pressure, okay, to 500 kilopascal. So there's a final pressure value. So that will be 500 kilopascal. Given that the mass density of water is 0.997 gram per cm cube, so mass density, or basically density, is 0.997 gram per cm cube. We're also told to determine the change in molar Gibbs energy. So this question is two. We have to find the change in Gibbs energy as well as the change in molar Gibbs energy of reaction. Now, the first thing you have to note is this. We have a question where we are meant to find the Gibbs energy and molar Gibbs energy. And for anyone who hasn't really studied well or might be confused, you have to note that the change, okay, in molar Gibbs energy is the same thing as the change in Gibbs energy divided by the number of moles. That is basically what this is. So, when you find the change in molar Gibbs energy, you can always find the change in Gibbs energy. And if you have the change in Gibbs energy, you can always find the change in molar Gibbs energy, provided you have the value for number of moles. So therefore, the change in Gibbs energy, okay, is the same thing as the number of moles times the change in molar Gibbs energy. So this equation that you're actually looking at is what the relationship between the molar Gibbs energy and the Gibbs energy is. So this particular equation. Now that we have that information, we can go back to the information that we're given. We're told the initial pressure, the final pressure. We also told the volume. And in this question, they did not tell us that we're dealing with an isothermal problem. So we're going to be using this particular equation to solve this question. The molar Gibbs energy at the final pressure, okay, is equal to the molar Gibbs energy at the initial pressure, okay, plus the molar volume multiplied by the P final minus the P initial. This is what we're supposed to use. We have the value for initial pressure, okay, we have the value for final pressure, we have the value of volume, but we don't have the value for molar volume, which is basically Vm. This gives energy at the final pressure and then gives energy at initial pressure. We can rewrite this formula this way. The change in molar Gibbs energy, the molar Gibbs energy at the final pressure minus the molar Gibbs energy at the initial pressure, okay, is equal to the molar volume times P final minus P initial. So the change in molar Gibbs energy, okay, is going to simply be the molar volume times P final minus P initial. So this is basically the equation that we're going to use in solving this question. Now, the next thing you're going to note is this. We're given volume in the question, but not molar volume. But we're also given density in the question, right? Well, we have to remember that the formula for density is what? Density is equal to mass over volume, right? So density is equal to mass over volume. When you cross multiply, what you end up with is mass is equal to density, okay, times volume. So what this is simply asking us to do is that we're going to go from just the density and the volume to discovering what the mass is. So you have this one right here. You have 0.997 gram per cm cube. So 0.997 gram per cm cube, okay, times the volume that we have. And the volume we have in this question is 100 centimeter cube. So times 100 centimeter cube. Of course, we do the cancel out. So we have 0.997 grams times 100. You end up with the mass 99.7 grams. Let's not forget that in order for us to go from volume to molar volume, we have to have the volume divided by the number of moles to give us the what? The molar volume. So this is how it's done. Now we have mass, okay? We have the mass. Now, you may be wondering, why do we have the mass? Well, because we have to determine what the number of mole is so that we divide, we use the volume to divide the value for number of moles in order for us to get the molar volume so that we can properly input it in this equation. So we're going to need the value for molar volume to be able to properly substitute. So now you have the mass. Well, one thing you need to also remember is the number of moles, okay, which is what we're trying to calculate, is the same thing as mass over molar mass. We've got the mass, right, which is 99.7. We know the molar mass because the molar mass of water can be calculated. So the molar mass of water, we know that to be 18.06 gram per mole. So that would be 99.7 grams, okay, divided by 18.06 gram per mole. And the reason why I don't think I need to calculate the molar mass of water is because this is an advanced chemistry course. So at this particular point, people already know how to solve molar mass. So we cancel our grams, 99.7 divided by 18.6 is going to give you the number of moles to be 5.52049 mole. So this is the number of moles is just basically 5.52049 mole. So this is basically what we're going to be using. Now, the work is not even close to being done, right? Because this question is would actually require much more complicated solution, but not difficult, just a little bit more complex. Not complicated, I apologize, complex. So rewriting our formula, let me rewrite it here so I don't have to go back and forth. Rewriting our formula, we know the change in molar Gibbs energy is what? The molar volume, okay, multiplied by P final minus P initial. Well, the molar volume, we still don't know what that is, but we have the number of moles. And we have to remember that the unit for change in Gibbs energy, molar Gibbs energy, is what? Joules per mole or kilojoule per mole. Note that when you find joule per mole or kilojoule per mole, you can either multiply by 1000 or divide by 1000 to go from either kilojoule per mole or joule per mole. So don't overthink it. But we have to remember that this question now, where we're given the molar volume as well as the pressure. We have to make sure that we use the values in which the units match in such a way that when we cancel out units or when we use our units, we're going to end up with joule per mole. So, for example, you have molar volume. Well, when we think about the SI unit for volume and how we can go from the regular parameters that we're given to joule per mole, we have to remember that the unit for volume is meter cube. Now we have molar volume, so we can say meter cube per mole, okay, times the unit for pressure, right? The unit for pressure is simply a bunch of different things, but we need the unit for pressure in such a way that we can manipulate it to get joules per mole, and that is simply Pascal. And another thing for name for Pascal is the same thing as Newton per meter squared. That is it, because pressure is the definition of pressure is force over area. So the unit for force is Newton, the unit for area is meter squared when you think about SI units, right? So simply cancel out meter squared here, cancel out meter squared in meter cube is just m. So we end up with Newton meter divided by mole. Remember, Newton meter is the same thing as joules, okay? And then you just have mole. Newton meter, the reason why it's joules is because the unit for energy or work done is joules, because what is the formula for work, right? Force times distance, and the unit for work is simply joules. So we can just say Newton meter is the same thing as joule, and then per mole will be joule per mole. So this, what I'm trying to tell you is that we have to convert our molar volume to meters. What I'm telling you is that we have to convert our molar volume to meter cube per mole, as well as the pressure to be either Pascal or to be in Pascal or to be in Newton per meter square. It doesn't really matter. So I'm just telling you that this is what we're going to use. So we're not going to be using any DM cubed, any atmospheres, any bars, or any mmHg or any centimeter cube. We're going to have to convert from whatever we have to what we need in order for us to get our units for change in molar Gibbs energy to be in joule per mole. So this is how it's done. Anyways, that's the important information that you have. Now, let's go back to the volume that we're given. 100 centimeter cube. Let me just do it on the side here. 100 centimeter cube, right? In meter cube is going to be what? Well, let's not forget that we note this, that 1 meter, okay, is the same thing as 100 centimeter. Then 1 meter cubed is the same thing as 100, okay, centimeter cubed. 1 times 1 is 1. Meter times meter times meter is meter cubed. I'm writing the fundamental information. 100 times 100 times 100 is just simply, what is it, you guys? What is it? You have 100 times 100 times 100. So you have centimeter cube. So what you end up with is 1 million centimeter cube. And then you have 100. Our question gives us 100 right here. So we're just going to have 100 centimeter cube. I'm using proportionality method to be able to solve this. Let's just call this X for our unknown. So that would be 1 million centimeter cube X is equal to 100 centimeter cube decimeter cube. So of course, cancel centimeter cube here, cancel centimeter cube here. So what you end up with is X is equal to 100, okay, decimeter cube divided by 1 million. So of course, cancel this out, cancel this out. So you have, so X is just going to be 1 times 10 raised to the power of negative 4. Okay. Oh, sorry, not decimeter cube. Gosh, the way the devil really wanted to mess this up for me. It's not decimeter cube. We have meters cube. So this is going to be meter cube here. So 100 divided by 1 million is the same thing as 1 divided by 1 divided by 10,000 meters cube, which is the same thing as 1 times 10 raised to the power of negative 4 meters cube. Of course, we know that this can be divided by the number of moles. So that's going to be divided by the number of moles. So basically, this is the volume, right? Divided by the molar the number of moles, because we're trying to go from volume here to molar volume. So this would look like the molar volume is going to be volume divided by number of moles. So that would be 1 times 10 raised to the power negative 4, okay, meters cube divided by the number of moles, which is 5.52049 mole. You guys can already see that this question is quite complex. So don't worry. At the end of the day, it's gonna make sense. I'm gonna do like a short review. So 1 times 10 raised to the power negative 4 meters cubed divided by 5.52049 mole is gonna give you 1.8114 times 10 raised to the power of negative 5 meter cube per mole. Okay, so that's it. Now, of course, you have P final minus P initial. You have the P final to be 500 kilopascal or 500,000 pascals. We already know Pascal is the same thing as Newton per meter square, so we actually don't need to do any. We don't need to we don't need to manipulate anything. So I'm just going to rewrite the equation. Change in molar Gibbs energy is going to simply be molar volume times P final minus P initial. So that would be change in G. Remember, Pascal is the same thing as Newton per meter squared. So let's not worry about that. We're just going to simply substitute for pressure because we don't actually have to convert the units at all. It's at the proper units that we want. So we have 1.8114 times 10 to the power of negative 5, okay, meter cube per mole, okay, times, so that will be, final pressure will be 500,000 Newton per meter square. So that'll be 500,000 because 500 kilopascal is the same thing as 500,000 Newton per meter squared, okay, minus the initial pressure, which is just 100,000 Newton per meter squared. So that's how it's done. So you have changing G of M to be 1.8114 times 10 to the power negative 5 meter cube per mole times 400,000 Newton per meter squared. Okay, cancel out meter squared, cancel out meter. So you have 400,000 times 1.811 times 10 to the power of negative 5 would give you 7.245 7 3 Newton meter per mole, or you can just simply write 7.24573 joule per mole. That's basically the answer. Now, I want to quickly mention something to you guys. The thing I want to mention is that because we're dealing with a question in chemistry, we have to put in the proper number of significant figures. And we have to look back into our question and see the number of significant figures for the numerical values in our question. So we have 100 kilopascal. So that's 3 sig figs, 3 sig figs, 3 sig figs. So that means our final answer would have to be in what? 3 sig figs. So the change in molar Gibbs energy is going to be 7.25 joule per mole as the answer to the question. Now, I wanted to also mention something. So, if you go back to our question, you notice that we're not simply asked to find the change in molar Gibbs energy. We're also told to estimate the change in Gibbs energy. Well, if you remember what I taught you, the change in Gibbs energy, okay, is the same thing as the number of moles times the change in molar Gibbs energy. So, that will be the change in Gibbs energy is now simply going to be the number of moles. We know that to be 5.52. Know that to be 5.52. I'm trying to look for it. We calculated 5.52049. 52049, okay, mole times, we're going to use the raw value. I'm not going to use the approximated value. The raw value is the way to go in chemistry. So times 7.24573 joule per mole. Cancel out the mole. 5.52049 times 7.24573. So the change in G is going to be simply 40 joules. And this is basically the answer to this question. Basically, exactly 40 joules. So yeah, this is the answer to this question. If you have any questions, please put in the comment section. If you have any concerns, also put it in the comment section. If you have a suggestion, also put in the comment section. Now, to keep my promise, I'm just going to quickly do the short review of what we did, right? So the question asked us to find the change in Gibbs energy as well as the change in molar Gibbs energy. So the first thing we did is for us to determine the formula we're supposed to use after we've brought out the parameters. We then determine the formula that we're going to use as the relationship between Gibbs energy and molar Gibbs energy. We have the formula we're supposed to use. Next, we have to determine the units that would work for this formula to work properly. So we notice that the unit for change in molar Gibbs energy is just simply joule per mole. So we had to manipulate the unit for volume to go to be in terms of whatever we are going to manipulate to get joules per mole. So that means we had to change from 100 centimeter cube for our value to whatever that value is in meter cube. And we know that value to be 1 times 10 to the power negative 4. So now we had the units for volume. We had to remember that the formula required us to use molar volume. So we have volume, and then from volume, we divided volume by number of moles to get molar volume. Now, to be able to even find the number of moles before molar volume, we're given the value for density. We have the value for density as well as value of volume. We're able to find the mass. And from the mass, using the molar mass, we're able to find the number of moles. So that was the number of moles that we used to determine the molar volume. So we have pressure. Pressure, thankfully, was in the units that would make our question work well. So we just simply substituted. And when we substituted, we did the calculation to get 7.25 joule per mole for the value of change in molar Gibbs energy. But then we also have to solve for the change in Gibbs energy, and then we used our formula, change in G equals number of moles times change in GM, and we've determined the change in Gibbs energy. So that is basically what we did. If you're a student who is struggling in any of your STEM related courses and you're trying to succeed, make sure you email me at shohabitutoring@gmail.com. I help middle school, high school, and college level students to succeed and be the best version of themselves in academia. You can also email me for mentorship services. I help students succeed in other areas of academia besides tutoring. So I wish you guys all the very best, and email me at shohabitutoring@gmail.com. Assalamu alaikum wa rahmatullahi wa barakatuh.